So welcome back. Bjørn Kjos-Hanssen is going to talk about automatic complexity as a measure of irregularity. Thank you.
Thank you, everyone.
People online, if you don't hear us or something, do something. I don't know. Write something in the chat.
Yes, so I'd like to thank the organizers of CCR for inviting me to come to this interesting meeting. And yeah, my talk is, well, it's not about computability exactly, but complexity. And so this topic comes from sort of outgrowth from Komogoro complexity, which is more closely in computability. Not sure what's the preferred way to advance the slides, but okay. Yeah, thanks. So yeah, Komogoro complexity is well known to this audience, and here in automatic complexity we study a different notion with some of the fundamental properties being changed. Right, so Komogoro complexity is not computable, but maybe depending on your taste or your purpose, a good notion of complexity maybe should be computable, because otherwise, you can only do these theorems and asymptotic proofs, but you can't really say what the complexity is in a more concrete way. It would also maybe be nice if the complexity is well defined, so I can say what's the complexity of 01101, for example, and not just have to say, oh, I'm sorry, it's only defined up to a constant additive term. So the third bullet point here is maybe more controversial whether this is a good thing, but so if you have a complexity notion that's not just computable but very efficiently computable, like just look at some very, very simple property that you can really quickly figure out, then maybe that's not, then it's not, it doesn't seem as general. And there could also be some connections. I mean, if you have this more, let's say, NP complete notion of complexity, there are some connections. Like there was a result of Liu and Pass from 2020 where they showed that certain existence of one-way functions in computational complexity was equivalent to the hardness of time-bounded Komogoro complexity. So there could be some value from that point of view. So if the complexity we're looking at is sort of NP complete but computable, then it's like we have to search and look for the witness to the complexity, but it's not an impossible task. It just takes a long time. Now let's see. So the last bullet point, it should be maybe robust. So this is the problem I also discussed with Avira right before the talk. Yeah, maybe we can make a definition like this, but it won't be robust. Like every tiny little change in how we make the definition leads to a different notion, and that's unpleasant. Yeah. So the automatic complexity will have some of these good properties, but robustness maybe not so much. To some extent, it's an open question. And as far as the NP completeness, it's known. Well, I proved this for automatic complexity of partitions rather than words, because that was a little easier to achieve. Okay, so maybe let's get into the definition of the central topic that we're looking at. Okay, so this might be familiar. So a deterministic finite automaton is sort of like a Turing machine, but it has a finite set of states, finite alphabet, and then a transition function that takes you from a state and then the next symbol in the input word that you're reading, and then you go to another state. And you start in an initial state, Q0, and then you accept the word if you end up in one of these final states. We can also look at the non-deterministic version Nfa, and this will give a different notion of automatic complexity, unfortunately. And so here, in a given state and reading a given symbol, we're not just going to another state, but we're going to a set of states, or there's a set of states we can go to. Okay, and so here's maybe also familiar definition for many people: the language recognized by a finite automaton. So we just well, there's different ways to say this. I think in some books, like Sipser's book, he doesn't define it this way, but he talks instead of like a sequence. Talks about a sequence of states that leads to an accepting state, but a little bit more formally, we can say that we will extend this transition function so that it takes a string as an input, and yeah, so if you extend the string by one more symbol, then you just go to where you were after reading the first all but one many symbols, and then follow the transition function. And the language recognized is those words where you end up in a final state. And this can also be done in a similar way for non-deterministic finite automata. Okay, but so here we get to the definition of automatic complexity. And this was defined by Shallit and Wang in 2001, or presented at a conference in Ontario in the year 2000, which was actually, this was unknown to me. So I independently made the same definition in 2009 when I was teaching a class, and I wanted some interesting final project for the students. But Mia Minnis told me that this had already been studied in 2001. So let's see. So we want to say that the automatic complexity is somehow the smallest DFA that somehow isolates the word X. Now, how do we do that? We could say it's the smallest DFA that accepts X. Well, then, then we can always just use one state and accept everything. Or we could say it's the smallest DFA that only accepts X, nothing else. But the problem is that these DFAs have cycles, and so then the number of states would always be the length of the word, which is not interesting. So the compromise that Shallit and Wang and I also came to is we can say, how about we want the only word of the same length as X that's accepted to be X. So we want to find a automaton that accepts X and nothing else of that length. Because that at least avoids those two objections that I raised. I mean, we could also imagine something like transducers that print the word X. That would be another option. But we're going to explore this definition. Okay, so as an example, and so to show that we can actually calculate this. So if I have a word that just consists of the same symbol repeated n times, then the complexity is 2. And the one nice thing is that we get it picture proofs. Okay, so here's the proof. We want to accept, which means we want to go in a state with this double circle. That's an accepting state. So we want to accept whenever we see zeros, but if we ever see anything else, so if this is now a language with alphabet 0 and 1, then anything else would be just a 1. Then we have to go somewhere else, and this can now be thought of as like a dead state, trash state, where once you're in state Q1, you will not accept the word, and so whatever you see after that, you stay in Q1. Okay, so it turned out that also the non-deterministic version of this, which wasn't studied by Shallit and Wang, is interesting, and in a way also sheds light on the deterministic version. Okay, so in order to define the non-deterministic automatic complexity, well, there's maybe more than one way to, but one way is to talk about state sequences. Oops. So, and then a state sequence is just a sequence of states where each one can be the next state while processing a certain word. So, and so an accepting state sequence for the word X is just the sequence where you start with the start state Q0, and then Q1 is something you can get to when reading the first bit of X, and then Q2 is something you can get to from Q1 when reading the next bit of X, and so on. And so P, let's say that P is the set of all accepting state sequences. This could also be formulated as the set of paths in a graph, or set of walks in a graph. Okay, but now in terms of this set, we can then define the non-deterministic automatic complexity. But let's first say that an NFA path uniquely accepts the word X if there is just one path of the appropriate length where X is accepted, and then for any word of the same length as X that's different from X, then there is no path like that. But there's no accepting state sequence. Yeah, and then we can define the non-deterministic automatic complexity to be the minimum number of states of an NFA that path uniquely accepts X. Oh yeah, Cartman.
Why do you want the uniqueness here? Why not just X is accepted and nothing else?
Oh, yes, this actually, the big open question is whether that is the same thing. Right, so you're anticipating the next slide. So, yeah, we can also write this as a path to emphasize that we're counting the number of paths, but yes, we could also consider the number of words. So let's say the non-deterministic word-based automatic complexity is the minimum number of states of an NFA that, with the same condition as we had for DFAs, it just accepts X and nothing else of that length. And then if you concentrate, you see that we have this one inequality one way, but I tried in several ways to show that these are the same or not the same. And by tried, I guess, I mean, I changed some of the definitions and then showed that now we changed definitions, these became different, so they could separate them. But with the original definition, cannot separate them. And it seems, it seems to have some number theoretic interpretation, as far as I can tell, certain properties of Diophantine equations with constraints. Maybe I can annoy the online audience by writing it on the board, but like a bound on how far apart they could be. Oh, I see. No, I haven't tried that. Yeah, it's that's a natural question. Yeah, so the kind of equations that appear are things like so you have some Diophantine equation, like, okay, this isn't necessarily going to be interesting, but then we have the constraint that, like, if z is positive, then y is positive. And if y is positive, then x is positive. And this is over n. And then what we're interested in is whether there is a unique solution, because what happens is that these automata, they look something like this. Like you have a cycle, maybe of length 2, 5, or 12. And we need to traverse this certain number of times, x, y, and z, and get to the accept state. And there should be only one way to do it in order for only one path to be accepting. And we can also have, let's see, this picture would have been better if I said that we had 5 here and then 12 here. So now it's like you can only go through the cycle of length 12 if you also go through the one of length 5, because otherwise you can't even get there. So that's where these constraints come from. Yeah, so these here could be other numbers. So it seems that if we had some very good understanding of this kind of system, that would really help. Right, and I think this is an important, interesting question, because the word-based complexity is the one that's the direct analog of what Shallit and Wang studied, and it's sort of easier to explain. Whereas the path-based version is the one that's convenient to use for computation, because you can just look at the transition matrix and talk about certain coordinate of a power of the matrix being 1. So it seems, I guess for the path-based complexity, the question whether it's below certain threshold is in NP, but for the word-based, I'm not even sure if it would be. Okay. Yes, and I think since this is the kind of thing you can compute, I think I did check that for words up to length 11, maybe there's no counterexample to this equality, but that doesn't mean much. Okay, so there's a lot of things that we now can do with this definition, and a lot of questions we can study. In particular, we can study whether these different complexity notions, how they relate to each other. So we have you have A and AN. So the one that's based on the DFAs and NFAs. So for computability theory, right, we're maybe more familiar with C and K, the plain and prefix-free Kolmogorov complexity, where there are many questions that can have analogs in the automatic setting. So one thing that I guess we can call comparative disagreement, for lack of a better name, is, so consider this statement here about C and K. So there exist words X and Y so that C is less complex, or X is less complex than Y, but Y is less complex than X. But in the sense of those two different complexity notions. Now, I thought about this, whether this is true, for a little while. I didn't come up with a proof, but I think maybe it's true, because you can do something like encode the length of X in the first few bits of X. So I think it's probably true. Somebody in the audience might have a definite answer, but we can ask the same question for some of these automatic complexity notions. So I mean, this is like a different from, or stronger way of separating C and K, right? To just say that C is different from K, that just says they give a different number on certain words. But this says that they actually like mix up the ordering of which words are more complex. Okay, and this can see. I suppose we can ask this for A and AN, but we can also ask it for states versus transitions, or vertices versus edges. Because the original automatic complexity is counting the states, but it's equivalent to count the edges in a DFA, because each state has a predetermined number of edges or transitions coming out of that. For each vertex, it's a regular graph. So for Shallit and Wang's original notion, it doesn't matter whether you count the states or the transitions or the vertices or the edges. But for non-deterministic, maybe it does matter. Okay, so let's make another definition for counting the edges. Yeah, so we define an edge in the natural way. And then we can say, let's say E sub n is the minimal number of edges of any NFA that path uniquely accepts X. So then the question is whether C and K, they can disagree. So can AN and EN disagree in the same way? So can you have two words where one word is simpler if you're counting the number of states, but the other word is simpler if you're counting the number of transitions? And yes, so here's just an example. This was found by computer search. And often, actually, what happens in this area is that you have your question, and you can ask, does something happen sometimes? And then you can even just do computer search and find the answer, and then try to understand the answer and make progress in the research that way. So it's sort of like you don't need to have a collaborator, right? I mean, in a lot of research projects, you have to have co-authors so that you bounce ideas off each other. But here, you can just search for an example, get it from the computer, then think about what you got. But on the other hand, the problem with that is that so now this example shows that we can have this comparative disagreement But it gives one example, and if you want to prove that there are infinitely many examples, right, then that's still definitely desirable in order to, in order to say that you really understand what's going on. Okay, but maybe let's see why this works. I thought this example is interesting, actually. So the one word X has 3 zeros and then some other stuff. Okay, and the other word Y of the same length has 1 more zero, so it starts with 4 zeros. And that means that we can use this automaton here. We can just loop with the 0 4 times, and then we can kind of hard code the rest like this. So that ends up taking 5 states and 5 edges. Now the other word, we can actually use fewer states at the cost of having more edges, because this word has a different pattern. So I didn't put the edge labels here, but they go like this. It's like 0 0 0. So after the first 3 zeros, you get to this looping state. Then you could do 2 1s and then 1 0 1. So then we're reusing this edge here. Right. So the word Y has kind of it requires fewer edges, maybe because it has this segment of many zeros. Whereas the word X requires fewer states because it has this a little bit more complicated, maybe more global behavior that you can reuse. Like this edge here is the second 0, but also the second to last 0. Yeah, so it's just a little example, but you can we should check that this makes sense, right? That there's only one path of the required length. So here the length is 8, and the start state is the same as the accept state. Okay, so how can we accept anything at all here with 8 moves, so 8 edges? Well, we have this structure of triangles, and this actually often appears in the examples found by the computer. And so that means that if we don't use this loop in Q3, then we have to have a multiple of 3 many bits or symbols before we accept. So we have to, in order to accept, we have to go here to Q3 and loop. And well, we can loop twice and then go straight back to the accept state. That will be 8 moves. And yeah, if you think about it, there's no other path of length 8 then. Okay. Yeah, so I've written a lot of papers about this now, starting in like 2015. And there's also a paper by Jordan and Moser that came out in 2021. So they look at normal infinite sequences and look at the automatic complexity of those. But, okay. So now I'm going to survey some of the results. And all these papers I've written in the last couple of years. What are some of the results? What are some of the unknown remaining questions? Yeah. So for example, so whether the complexity is below a certain number, that's in NP, and we don't know if it's NP complete. Right, but then I was able to show that these kind of related questions are not context-free, or in the complement is not context-free. And also starting to understand a little bit about circuit complexity, and show that it some related problems cannot be done by semi-unbounded fan-in constant depth circuits. And I was able to construct some a modified definition where we talk about automatic complexity of equivalence relations, and there I can show it's NP complete, but it's not that close to automatic complexity of words. Okay, so let's see. So I should say then what circuit complexity is. Okay, so here is a kind of a silly example, or redundant example, but this is a circuit that computes the projection function that just takes x1 and x2 and gives you x2. So you have the inputs here at the top, and then the circuit, can I think of like an electric circuit? You take x1 and x2 and you compute the and then this piece of the circuit computes the and of x2 and not x1. And then if you take the OR of those, well then, okay, that's just x2. As far as the semi-unbounded part, that is saying that we can have unbounded ORs like this, but we cannot have unbounded ANDs. So semi-unbounded is sort of like a sigma 1, but not pi 1. Okay, so we have a picture of some results there. So let's see. So we try to define an appropriate language, and the language, or the set of strings, is supposed to capture this the problem, like computing the non-deterministic automatic complexity. So we can ask whether the complexity is more than the length divided by a certain number. So then we get problems like L2, 3. So for binary words, is the complexity more than 3, or length over 3? And for ternary words, is the complexity more than the length over 2? Okay, and there's a big gap here between what I was able to do and what one could try to do, because these these classes here. Let's see. Oh, I should also say that the dotted arrows are non-implication. So L23 and L32, they're not in these very simple classes at the bottom, but they are in co-NP and E, which means computable in like single exponential time. But a question that was also raised by Shallit and Wang is whether they would be in P. Yeah, now it might seem a little unmotivated here. Why is this L23 and L32? So let me get to some results that explain that. Right, so let's see. If we consider just the complexity divided by the length, that's a kind of a complexity rate. Okay, so what are the results? So for almost all words, for random words, you could say, this complexity rate is no more than 3/4 plus epsilon. And more, they can be generalized to other alphabets, which I did. And how about an upper bound that works not just for almost all words, but for all words? So Shallit and Wang, they have this upper bound that, so if n is the length of the word, then complexity, I mean, there's sort of a trivial upper bound of n, but you can get it a little bit less. So n plus 2 minus basically the log. It's like n minus log of n. And so the way they did that is they say, well, there has to be certain repeated subwords, and we can exploit this by looping back and reusing some of the states. Okay, and then in preparation, I have a result that improves this slightly. That says we can get something like length of x minus square root of x. But it's still a question, though, whether maybe is it even the case that the complexity, automatic complexity, gets close to the length of x at all, or does it stay more in the region like length of x over 2? And so yes, maybe to get to the point there for why do we care about the length over 2? So my master student Kaylee Hyde showed that the automatic non-deterministic complexity is always bounded by the length over 2 plus 1, and that is by the following picture. So what she said is that, well, you can always reuse states, but without reusing any edges. So here, for an arbitrary word, we can't maybe assume that any of the edges or any of the symbols are going to be repeated, but we can just lay it out like this. And so the reason this works is similar to what I said about the triangles earlier, because now this word is of odd length, and we're starting and also supposed to be ending in the same state. And so you see we have, if we go sort of partly through this, but not all the way to the end, or all the way to the right and then back, then we're going to end up using only an even number of symbols. So if the word has odd length, we definitely have to use this loop here at least once. And then the way this is designed, there is no time to use this loop more than once before you have to run back to the final state. Okay, so that's why this construction always works to give an upper bound of basically n over 2 on the number of states. And that's if the word has odd length, and if it has even length, you can just do one of these sort of trivial modifications where you just say, let's just add, at the cost of adding one more state, we'll either at the beginning or the end, we'll do it like this. Okay, but the nice thing about this is that it's sharp in some way. And yeah, before even stating that, let's just anticipate that by saying that the deficiency, complexity deficiency, is the difference in Hyde's theorem. So the difference between this upper bound and the complexity. So then it was shown by Shallit and Wang that if you have a square free word, then the complexity is always at least n over 2 plus a half. Okay, and then this works out to saying that square free words have a deficiency of 0, so the Hyde's theorem is sharp. But now square free words are the ones that don't have any square, and so for binary words there are not very many of them, because it's like let's see. Yeah, so let's draw the tree of all the square free binary words. So we could have 0 and 1, and then I'm not allowed to do 0, 0 because that would be a square. But we can do 1 and get to 0, 1. And then similarly here. Okay, and then 0, 1, so I can do 0, 1, 0. I cannot do 0, 1, 1 because that would involve a square. yeah, we sort of don't need this side because by symmetry, this side is the same. So let's forget about that side. Yeah, so this 0, 1, 0 is the only thing we have so far. And now if we go to 0, 1, 0, 0, then that has the square of 2 zeros. 0, 1, 0, 1, but that has the square of 0, 1 is repeated. So actually that's it. Those are the only square-free binary words. But for ternary words, you can have an infinitely long one, as was shown by Tua. Okay, and then so how about some serious theorems here? So this is like my bragging slide. So Shallit and Wang showed that the complexity is at least n over 13 for almost all binary words X. And they also stated that Holger Petersen had told them that this could be improved to showing that the complexity of almost all words is at least the length over 7. And here almost all just means that as the length goes to infinity, the fraction goes to 1. Okay, and then in a paper published last year, I showed that for almost all words, the complexity is at least n over 2 plus epsilon for any epsilon greater than 0. Right, and we also have this upper bound. Yeah, I mean this actually also works for the non-deterministic complexity. So because of the Hyde's result, it's we have a sort of sharpness there, that the complexity is below n over 2, but it's above n over 2 plus epsilon. Okay, now how did this work? So here is the sort of the main idea for how this proof worked. So sort of already hinted at it in this drawing here, that these automata that we get for automatic complexity, they are like have these cycles that are connected in a certain way, and even they should be connected in a tree. So we shouldn't really have that cycle that sort of goes like this, because then we can quickly get a non-uniqueness that you could either do this and this, or you could do one thing first or the other thing first. And I thought was also neat and maybe appealing to this audience is that the way that these trees of cycles are generated as you go through the processing of the word, it creates this tree of cycles in the Kleene-Brouwer ordering. So let's see if we can see that in this picture. So here we have this kind of complicated word. So there's another example that was found by computer. So 5 zeros. Okay, so yeah, so globally, what do we have here? We have a cycle here with the start and the accept state in it, Q0, Q3. And then we have another big cycle kind of stacked on top of that here. And then we have 2 more cycles stacked on top of those. We have a triangle here and a 2 cycle of length 2 over here. But if we just start, if we are given the sequence of states we're supposed to follow, and we just read the word symbol by symbol, then it's like initially we don't know what the whole tree is going to look like. So initially we just see 0, 0, 0, 0, 0. So we have gone from Q0 to Q5, but nothing has, there's no cycle yet. And then we have a 1 and a 0. Okay, but now we start to loop back. So now we go 0, 0, 0 here. So then at this point, the tree has just this one. It has a stem, and then it has a 1 cycle here. But then after that, we go over here and we get 0, 1, and then we repeat some ones here. So now we have two siblings in our tree. We have this cycle of length 3 and this cycle of length 2, but with no common cycle as their parent. Okay, but then we come back here and go to Q5 again. And at this point, we've created I guess, a 6th cycle that's a common parent, a common ancestor for those two. And then finally, we go from Q5 to Q0. Now we created a new common ancestor for all the previous cycles. Yeah, and this picture fits the general framework on this board here. That so the equation would be something like 3x plus 2y plus 6z plus 6w, and then with the constraint that if x is greater than 0, then so is z, and if y is greater than 0, then so is z, and if z is greater than 0, then so is w. Yeah, and so once you have this way of looking at it, then analyzing the complexity of almost all words can be done by also saying something about just thinking probabilistically about how many repeated cycles will there be in a random word. So that's maybe the other ingredient for this theorem here. Okay. Maybe check how we're doing on time. 10 minutes. Yes, almost all right. So it means that the fraction of words of length n goes to 1 as n goes to infinity. But there's some fine-tuning that's left to do there, because you could say, well, there's still a big gap maybe between n/2 and n/2 plus epsilon. And what about like n/2 minus square root of n or something like that? Okay, now we can once we have this framework, we can these definitions, we can look at complexity of all kinds of words. So like cube-free words, overlap-free words, whatever that is. So I guess the way I look at it is, it's like in computability theory, right? We have the different amounts of non-computability, basically, right? We have the generic sets, and we have the iterated halting problem, and simple sets. We have different signposts for like how complicated something is, and then we can study comparing them in all kinds of ways, like Weierau reducibility or Turing reducibility. And we can look at applications to other areas of math, and we can also sort of apply the computability to itself by saying, how complicated is Turing reducibility and computability theoretically. And so analogously here, we can ask questions like, well, let's just pick our favorite class of words and then find the automatic complexity of that kind of word. Or we can compare different variations on the definition of automatic complexity and see how they are related to each other. And we can also look at in a sort of more meta way, you can say, let's look at the complexity of automatic complexity itself, like how hard is it to compute. Yeah, so here are some examples, cube-free words, overlap-free words. Maybe I won't define what they are, but just some examples. Okay, and so here are some computer results. So the Hyde's theorem said that the complexity has this upper bound, and which is sharp. And actually, here are some results on whether that bound is achieved. So this says that the dn is the deficiency, so that can be 0. So a little different from Kolmogorov complexity, right? We have this notion of deficiency here, that where deficiency is 0 means that the word is as complicated as it can be. And actually, a lot of words are like that. So if these numbers here are close to a half, the fraction, it's a little different depending on whether the word has even or odd length. But experimentally, what this is saying is that, yeah, about half of all the binary words have the very maximum complexity. So not just, my result says that it's at least n over 2 plus epsilon, but this is saying it's actually literally the very upper bound. That is the complexity of about half of all words. Which is a little strange, but my best sort of explanation of that is that this picture here is like, even though this applies to all words, it can still be this picture can sort of be competing with other automata that you may want to make. And then the phenomenon is that for about half of all words, there is no better automaton than this. Yeah, it would be unfortunate if I didn't get to this. So Jordan and Moser has this new paper where they look at the automatic complexity of normal words, which are words where the frequency of a particular subword is as expected by if you generated a word by flipping a coin. So it really makes sense for an infinite word to say that it's a normal word. So it's like the normal number in number theory. And so if you have a normal word, you can define, well, if it's an infinite word, then you don't want to just look at the automatic complexity of just a single string, but a finite string, but you can look at the lim_in for lim, this should be sup, or lim sup of the automatic complexity rate. Okay, so Jordan and Moser, they started with saying, well, maybe this lim_inf is always 1 for normal sequences, but they actually showed that there's a normal sequence where the lim_inf is 0 and the lim sup is no more than 1/2. We can, let's see, we can easily observe that the lim sup is no more than 3/4 for random words. And then I have a result in preparation that says that actually for all normal words, this lim_inf is no more than 3/4. And the proof idea is, so this Cayley graph, that's this picture that I keep going back to. Let's see, let me show it again. Yeah, so since this was found by my student Cayley Hyde, I call it a Cayley graph. And that is a useful tool for proving this result. So to show that for all normal words, this I of t is no more than 3/4, we can argue that if you look at a Cayley graph for the word, then, well, see, the problem is that may not be deterministic. Yeah, so right, so even in the deterministic case, we could consider something like this. I mean, we should maybe add on another state to make sure that it's also a total DFA. Or something like this. But there is the danger with the intermediate states that they may not be deterministic. But maybe we have a 0 here and a 0 here. Now this is non-deterministic. But then you can start to analyze, well, how often is that going to happen? And the thing is, when it is non-deterministic, there's a simple fix. We can just split this state in two like this. And now it's deterministic, but now we have one more state. So we just have to worry about how often do you have to do that. So then what I'm arguing for this result is that, so if you take either the Cayley graph or you take the shifted Cayley graph, which means the one where you kind of hard code one symbol and then take the rest of the word after that. Or maybe you hard code one symbol at the end. Then it can't be the case that things go wrong too often for a normal word. And in fact, so I only need to know that the word is sort of weakly normal in the sense that it has normal frequency of occurrence of these words of length 2. Because if you have, I guess I'm not going to repeat the argument, but okay. Okay, so there's some other, let's see. There are other topics, but I'm not going to go into all of them. Let's see. Yeah, so I also studied Fibonacci words. Just as an example, you can take your favorite kind of word. The Fibonacci words are words where you have a sequence of words, and the next word is the concatenation of the two previous ones. So it's like the Fibonacci numbers. And the length of the nth Fibonacci word is the nth Fibonacci number. You can also study the shift registers, which are used in engineering for cryptography. And there I showed something like that the automatic complexity is at least n over 2 minus a small amount. Also interesting, actually, is the Fibonacci words, not Fibonacci words, but you take the sequence of Fibonacci numbers mod a particular number. And yeah, if I have time, maybe I'll draw a picture for that. Okay. Yeah, no, okay. Yes, okay, but in any case, okay. So yeah, so thank you and everyone for coming to my talk.
Well, maybe we have time for a quick question or comment. Yeah.
Going back to the like you mentioned earlier in the talk when you're trying to compare the complexity with unique paths versus the complexity with an arbitrary number of paths. You say you take that up to length 11.
Yeah.
That seems like to be very impressive because if you report the number of automatas you have to take is gigantic. If you have like any fun
but I'm using these state sequences, so it means I'm not searching through all NFAs in like a really naive way, but just saying, if you look at the accepting path, that has to generate the whole NFA. So you can only search through those. And of course, you can do little things like say, well, you may assume that you start in Q0 in state number 0, and whatever it goes to next is state number 1, and you can remove some symmetries like that. But but it's still, I think the running time is sort of like 16 to the n, where n is the length of the word.
This is interesting. Okay, since it's our first day, and I'm not sure how this lunch arrangement works, let's stop here and meet back at is it 1:30? Okay, thank you very much.